This is the podcast for Discussion 3.1, Introduction to Organic Nomenclature. So first we have to talk about some basic vocabulary. So the first thing is, what is an alkane? And you probably learned this in Chem 1, but just in case. An alkane is a hydrocarbon with only single carbon-carbon bonds. Okay, so hydrocarbon meaning it just has hydrogen and carbon. The general formula for a hydrocarbon is if I have N carbons, that means I have 2N plus 2 hydrogens. And let me show you why that makes sense. If we look at propane, it has its 3 carbons in a row. Each carbon is attached to 2 hydrogens, and then the end carbons need 1 additional hydrogen. So that's why it's 2N plus 2. And that'll be true no matter how many carbons are in the chain. So some common examples that you've probably heard of: octane, fuels our cars; butane, if you've ever seen a butane lighter; and propane is in gas grills. Prefixes that you need to know: the prefix for 1 carbon is meth, 2 is eth, 3 is prop, 4 is bute, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is known, and 10 is dec. The really tricky ones are the first 4, because after that there's prefixes that you've seen before. So when we name alkanes, and this looks like a lot of information, but we're really going to break it down through examples, the first thing we have to do is find the longest chain of continuous carbons. So if you put your pen on the first carbon in the chain, it'd be the longest chain you could draw through without picking up your pen. Okay? You're going to pick the right prefix for that and add the suffix ane. Now, if you have any branches coming off of there, you are going to use a number to identify which main chain carbon the branch is attached to. So if I have 6 carbons in a chain and I have a little branch coming off the second carbon, I would choose the number 2. You're going to name the branch with a prefix for the number of carbons in the branch and the suffix YL. So like methyl if it's a 1-carbon branch. If you have multiple types of branches occurring, like 2 methyl branches, you're going to use more than 1 number to indicate the position and standard covalent prefixes to indicate how many branches there are. You can number the carbons in either direction, but your goal is to give the substituent groups the lowest numbers possible. So all that said, let's look at some examples. It's a lot simpler than it seems from looking at that slide. Okay, so clearly the bell is ringing. Okay, so when we look at the first example, I see that the main chain has 5 carbons, okay? So I would call this pentane. Now I do have 2 branches coming off the main chain, and they're on the second and third carbons, okay? So I would name this 2,3-dimethylpentane. Okay, so I want you to pause this and see if you can apply these rules to name the remaining 3 alkanes, and then we'll go over it. So pause and try them, and then we'll go over them. Okay, so let's talk about these. Check your work. The second one is butane. That's pretty straightforward. It's just 4 carbons in a chain. For the next one, when I count the carbons in the chain, the main chain, there are 6. And then I have a 2-carbon chain coming off of the third carbon. Okay, so I would call that 3-ethylhexane. Why ethyl? Because that substituent chain has 2 carbons in it. For the last example, the carbon chain has 1, 2, 3, 4, 5, 6 carbons in it again, so it's hexane. And then on the second carbon, there's a 1-carbon chain, so I would call that 2-methylhexane. Now, it's actually much easier to go from the name to drawing the structural formula rather than the other way around. So I want you to pause this for a second and see if you can draw these formulas based on what we already know. Okay, so let's go over these. So hexane, we know that's just 6 carbons in a chain, and then we have to add the appropriate number of hydrogens. Sometimes people will leave out hydrogens or try to draw too many, but remember that carbon always makes 4 bonds, so you need to give it enough hydrogens for that to be true. Okay? 3-methylpentane. Okay, so I have my 5 carbons in a chain, and then on the third one, I'm going to draw a methyl group, which is a 1-carbon group, and then 3-ethyl-2-methylpentane. Okay. Now the reason I wrote 3-ethyl first is that we normally alphabetize the substituent groups. Okay, so it got a little cut off here, but you can see there's 5 carbons in a chain. That's pentane. On the second carbon, we have a methyl group, so a 1-carbon chain. And on the third carbon, we have an ethyl group, which is a 2-carbon chain. Okay, now one of the words that you've heard me use is structural formula. That means that I'm drawing out the formula, I'm showing every single bond. A structural isomer, these are compounds with the same molecular formula but different arrangements of atoms. Okay, so let's think about trying to draw all the structural isomers of the compound with the formula C6H14. So that's the general formula for hexane. Right, now, you might think that there's a whole lot of isomers of hexane, right? It seems like there would be with 6 carbons. But when we actually look at it, it's not so much. So the first one's pretty obvious, right? Straight chain hexane. All right? Now, if I remove 1 carbon from the end and make that a substituent, I can come up with at least a couple more isomers. Okay, so I can make a 5-carbon chain and put my extra carbon group onto the second carbon. All right, so that would be 2-methylpentane. So hopefully you guys can see how that's an isomer. You can actually pause this and count and prove to yourself it's the same number of carbons and hydrogens. Okay? I could make another isomer by putting that methyl substituent onto the 3rd carbon. Okay? So that's 3-methylpentane. Now you might be thinking that I can make yet another by putting it on the 4th carbon. However, that's actually not a new isomer. That would still be 2-methylpentane, because in that case we would number from the right to give the lowest substituents possible, substituent numbers. Okay? So we have no more methylpentane isomers, so let's try taking off 2 carbons. Okay? So I put this in condensed form so you can see it a little easier. All right, this is an example of a butane based chain. So there's 4 carbons in a chain. So we would call this 2,3-dimethylbutane. Okay? I do have one more option with the 2 methyl groups. I can put them on the same carbon. So I would call that 2,2-dimethylbutane. And you'll see that you might try to move these around in other ways, but no matter what, you'll see that it's still the same as another isomer we've seen. For example, if we put those 2 methyl groups on the 3rd carbon, it would still be the same thing, right? Because we'd number from the other side. It would be 2,2-dimethylbutane. Okay? Sometimes people want to put these methyl groups on the end of the chain, but remember that would just lengthen the longest chain. So then we'd be back to having a methylpentane or even hexane. Okay, now, when we have these different structural isomers, we can see some trends. One of the main trends we see is a trend in boiling points. So as branching increases, so like hexane has no branching and dimethylbutane has a great deal, the boiling point will decrease, okay? And there are the names there for you in case you wanted to see them. All right, so as branching increases, boiling point decreases. All right, so you might wonder why this is, okay? Straight chain alkanes can pack more tightly together, which strengthens their intermolecular forces. So basically, imagine like long strands of spaghetti getting tangled together. That's one way you can think about it. If you can also imagine hugging somebody. If you were to hug somebody, you could get really close to them, right? If you were to be holding a giant box and try to hug somebody, you wouldn't be able to have as many points of contact, so you wouldn't be held together as closely. It's kind of a weird analogy, but it sort of works. Okay, so I want you to try this question, pause for a sec, and see if you can figure out which of the following are isomers of pentane. Okay, so let's talk about this. Now, the first one, 2-methylpentane, is not an isomer. All right, and here's why. 2-methylpentane is actually an isomer of hexane, right? Because it has 6 total carbons. And if you draw it out, it's a lot easier to see that. Methylbutane is going to have 5 carbons, 1 methyl group, and a chain of 4. And dimethylpropane will also have 5 carbons, 2 methyl groups and a chain of 3. So your correct answer would be C, okay? Now, you might be like, they are missing part of that name because methylbutane needs a number. Actually, not so much. So methylbutane doesn't need a number before the methyl group, because if you think about butane, it's a chain of 4 carbons. The only possible position a methyl group could be, if there's just one, is on the 2nd carbon. Okay? Because if it's on the 1st or 4th, it lengthens the chain. If it's on the 3rd, we'd number from the other side, and it's really the 2nd. Hopefully that makes sense. A little hard to explain in words, but I can happily show you. Same thing with dimethylpropane. If I have 2 methyl groups on propane, the only place they can be without lengthening the chain is the central carbon, so we don't need to specify a number. Okay, now these structures can get really large and really complicated, so a lot of times rather than drawing out giant structural formulas, we condense them, okay? So you'll see parentheses a lot. Parentheses usually mean a separate atom or atoms, group or groups that are bonded to a carbon atom. If there's a subscripted number after it, it sometimes can mean a repeating group. Okay, so I'm going to show you a couple of these that are condensed and then written out. So in the first example, it has an OH in parentheses. So that means it's bonded to the previous carbon. So it would look like that. Okay? 3 carbons in a chain, and the second one has an OH group bonded to it. All right, and then in the next one, that first set of parentheses is a 2 after it, and that's going to be a repeating group. They can't be bonded to the previous carbon because that carbon, well, both of them can't be, because that carbon already has 3 hydrogens, so it can only make 1 additional bond. Okay, so that one's going to look like this. This is going in the opposite direction as it's written, but don't let that deter you. It's still the exact same thing. Okay, so finally, things written after a carbon are usually attached to that carbon. So in this next example, I have C and then O. Now this is a little tricky, right? Because it's hard to know what kind of bond to make to that oxygen. But if you think about it, that carbon, that second one, must be bonded to the previous CH3 group, right? And then it has to be bonded to the CH2 group after it. So carbon needs to have 4 bonds. So that carbon must be double bonded to the oxygen. Plus, as we know from Chem 1, oxygen likes to make 2 bonds. And I know this got a little cut off in the beginning. Sorry about that. Okay, so I want you to practice these. Try to do this. The first one, I will say, is a little bit tricky. So, give it your best shot. Remember that hydrogen makes 1 bond always, and oxygen has a tendency to make 2 bonds, and we know carbon makes 4. Okay. So the first one, we have COO. When we see 2 oxygens written like that, typically one of them is double bonded to the carbon, and the next is single bonded to it. Okay, and then the last one looks like this. Oh, the hydrogen got cut off on the bottom, but that bottom carbon has another hydrogen bonded to it, okay? So we see that the CH2, CH3 groups, there's 2 of them bonded to the 4th carbon. Okay, homologous series of alkanes. All right, so a homologous series is any set of different molecules that are members of the same chemical family. So we could just be looking at alkanes, methane, ethane, propane, butane, alcohols, carboxylic acids that differ only by the number of CH2 groups. So one example would be methane, ethane, propane, butane, as I said. We could also look at a homologous series of alcohols. So we have methane, or excuse me, methanol, ethanol, and propanol, okay? As the chain length in a homologous series increases, so does the boiling point, and this is because of increased intermolecular forces. Now, it makes sense that as molecules get larger, that they'd be held together more strongly, right? Because intermolecular forces are additive, right? So if we're talking about something like dispersion forces, they're very weak, but the larger a molecule is, the more dispersion forces there are, and so the stronger the intermolecular forces. So in general, the bigger a molecule is, the stronger its intermolecular forces will be. Okay, when we name alkenes, because we've talked about alkanes, alkenes are hydrocarbons that contain 1 or more carbon-carbon double bonds. So the general formula for an alkene is if I have N carbons, I have 2N plus, or just 2N hydrogens, okay? That's if there's only 1 double bond. We name these just like alkanes, except the suffix is -ene, which makes sense, they're alkenes, so we end it in -ene. And the double bond location has to be given a number. Because if you think about something like pentane, there's multiple carbon-carbon bonds. So we want to say which one is the double bond. So the number goes between the prefix and the suffix. I'll give you some examples of that. The carbon-carbon double bond naming takes number precedence over any branches. So my goal is to make that the lowest number possible regardless of what else is there. All right, so this guy looks like, it's a 4-carbon chain, so it's butene. But we want to indicate that it's the second bond that's a double bond. So we would call that but2-ene. All right, now this guy is a little bit more complicated, right? Our longest chain is 5 carbons, so it's pentene, right? All right, so we would call this 4-methyl-pent-1-ene, because remember, we're going to give precedence to the double bond in numbering. So 4-methyl-pent-1-ene. All right, alkynes are hydrocarbons that contain one or more carbon-carbon triple bonds. So the general formula is if I have N carbons, I have 2N minus 2 hydrogens. So you see that these general formulas are decreasing by 2 hydrogens every time we add a bond, which makes sense, right? Because if I add another bond in between 2 carbons, they've each lost 1 hydrogen, okay? We're going to use the exact same rules as alkanes and alkenes, except the suffix is YNE, so -ine, and again, we're going to give number precedence, okay? So in this example, our longest chain is 5 carbons, so that's going to be pentyne, but again, we need to say where that triple bond is, so we would call that pent2-ine. Okay, now, this has only 2 carbons, so it's ethyne. Now, I didn't put a number because there's only one possible place that that can be, so I don't need a number to indicate that. Okay, good luck. Yay, we're done.